Hi, Assalamualaikum and a very good morning. Welcome back to the tutorial of 4.3 with Sir Haikal. Last time, you have watched a video regarding 4.3, which is orbital overlap and hybridization, it is much more focused on the concept and the idea presented quite holistically regarding overlap and hybridization. But in this video, we will focus more on the key terms and the key concept presented, and I will also show you some example regarding this idea of 4.3. Let's get started. Okay, first, we need to know what hybrid orbital really means. So as what we have learned last time, hybrid orbital are basically mixing two or more orbital in order to form a new set of hybrid orbital. You can imagine it as a car where the car uses a fuel and a car that fully uses an electric source. So when you mix this both technology, you will produce a hybrid car where the hybrid car can use both electric and fuel in order to move around. In the idea of orbital, we are trying to form a new set of hybrid orbital as the new hybrid orbital are much more stable orbital and it is consistent with the molecular shape that we have learned in 4.2. Now, let's look some example on how the new set of hybrid orbital can be produced. So let's say if you want to produce sp hybrid orbital here, you need to mix one s orbital with one p orbital. And this will produce sp orbital. But how many of them will be produced? So in order to visualize this, I think the best idea is to use an analogy. Let's say if you have 1 liter of a paint that is yellow in color, this is presented by the s orbital. At the same time, you have 1 liter of the paint which is blue in color. This is to represent p orbital. When you mix 1 liter of the yellow color, which is S, and 1 liter of the P color, which is P, you will produce a new color. Which is green. Okay? Instead of getting 1 liter, you are basically getting 2 liters of the new color. Because 1 liter plus another 1 liter, you will get 2 liter of that. And then, the sp orbital basically refers to the central atoms, where the central atoms bonded with how many pairs of electron. And then, referring to the number here, we can predict the molecular shape that it will produce. Since we have two sp orbital, we will have two bonding pairs. So we write it as AB2. Now, AB2, as what you have learned in 4.2, you know that it will carry a shape of linear. So you will draw it as linear. And the 2sp here means you have two lobes, sp1 and sp2. And hence 2sp as shown here. Now, same case for sp2. For producing sp2, we need to mix s orbital plus p orbital plus another p orbital. And hence, we can produce sp2. And we don't only produce one sp2, but instead, we produce 3sp2. And as what you will expect, because it produced 3sp2, and hence our class of molecule going to be AB3. And hence we have 3 lobes, where it carries the shape of trigonal planar. So we have 3sp2, so we're going to have 3 lobes. 1 sp2, 2 sp2, and 3 sp2 in the shape of trigonal planar. And for the others, I think it is quite self-explanatory to you. You will expect the same thing according to its molecular geometry. So here, it's basically S plus P plus P and plus P. And you will get 4sp3 and AB4. The structure going to be tetrahedral. And for this one, S plus P, and this one going to be 5sp3d, and this going to be AB5, which carries the shape of trigonal bipyramidal, and you will draw it as usual. Okay, let's look for the example next. Okay, let's say if we have a molecule of SF6, first, in order for us to draw the orbital overlap of the hybrid orbital, we need to draw the most plausible Lewis structure as what we have seen in chapter 4.2. Now, let's do the Lewis structure first. So as sulfur has 6 valence electrons. Meanwhile, fluorine has 7 electrons, but we multiply by 6 because it has 6 fluorine. So total, it has 42, and 42 electron plus 6 electron from the sulfur, we have 48 electron. Now, we need to draw the Lewis structure. So between S and fluorine, sulfur will become the central atom because sulfur is the more electropositive atom in the molecule, meanwhile fluorine is the most electronegative atom in the molecule, and hence will become the terminal atom. So let's draw that. So we have S in the center, and then it bonded with 6 fluorine. Okay, since it makes 6 bond with fluorine and 1 bond represent 2 electron, so the total number of electron that has been used is 12 electron. So left is 36 electrons. So the 36 electron will be used to fill up the terminal atom so that it is octet. So let's start. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So 6 electron multiplied by 6 fluorine atom. So we have used up all the electron. 6 electron, and we have no valence. And if we want to check that we have drawn a correct Lewis structure, we must count the formal charge. Sulfur. So in order to count the formal charge of the sulfur, sulfur has 6 valence electron multiplied by a minus with 6 bonding pairs minus 0 lone pairs electrons. So the formal charge is going to be 0. And then for fluorine, because fluorine, the formal charge of fluorine at each atom is the same, so we can just only focus on one fluorine. Let's say I take it here. Okay, so fluorine has 7 valence electron, minus 1 bonding pair, minus lone pair electrons. So we need to count the lone pair electrons. We need to count it one by one. 1, 2, 3, 4, 5, 6. So minus 6. So we got 0. So the formal charge of fluorine is 0. Sulfur is 0. So you know that when the formal charge is closest to 0 or equal to 0, it is the most plausible wave structure. So now you have confirmed that you have drawn the correct plausible wave structure. Hence, you need to give the class of the molecule first, where A becomes the central atom, and then it is bonded with 1, 2, 3, 4, 5, 6. So it's going to be AB6, where it follows the shape of octahedral. So let's say you didn't draw the structure correctly, you have to ensure that you convert it to the correct structure. For my case, because I've already drawn it correctly, so I don't have to change the shape once again. Alright? So let's say if you make your structure something like 1, 2, 3 there, 1, 2, 3 there, you have to convert into the correct structure first, then only you proceed with the next stage. Alright? Now this is an extra for you, which is polarity. So in order for you to determine the polarity, you need to determine the bond dipole first. So S and fluorine is a much more electronegative atom. So the bond dipole will go more on the fluorine. The electron density will move towards fluorine. And this is the same for all the cases. Okay. Now, you can see that when the bond dipole goes at one angle here, and the bond dipole goes to another angle here, it will produce a resultant force at this side, something at the middle. And same goes to this case. It will produce a bond dipole going to the right hand side. So since it is made up of the same atom, so the pools of electron density are equal. So hence, let's say if I have here 10 Newton on the right hand side, I will also have 10 Newton on the left hand side. So I can say that the left hand side and the right hand side can be cancelled out. At the same time, the above and below are also symmetry. So the above bond dipole and the bottom bond dipole can also be cancelled out. And hence, I can say that mu is equal to 0. Hence, it is a non-polar molecule. Okay? So this is the idea that you have learned in 4.2. Now, in 4.3, you need to convert this kind of drawing in terms of orbital overlapping. And the central atom, you need to draw the hybrid orbital. Let's do that. Now, in order for you to determine the type of hybridization, it depending on how many bonding pairs that they make. So here it makes 6 bonding pairs because AB6, right? 1, 2, 3, 4, 5, 6. Hence, the orbitals, the type of hybridization that happens at the central atoms are sp3d2. 1, 2, 3, 4, 5, 6. sp3d2. If it makes 2 pairs 2 bonding pairs, it's gonna be sp. If it makes 3 bonding pairs, which is trigonal planar, it's gonna make sp2. If it makes 4 bonding pairs, it's gonna be sp3. If you're gonna make 5 bonding pairs, it's gonna be sp3d. And if it has 6, as shown here, 6 bonding pairs, it's gonna be sp3d2. It is consistent to what we have learned just now. Okay. Now, to make the hybridization happens, we need to draw the orbital diagram for the central atom first. As you know, sulfur has 16 electrons. So, the electronic configuration of sulfur is going to be 1s2, 2s2, 2p6, 3s2, and 3p4. Since the idea of this hybrid orbital is based on the valence bond theory, so we're only going to focus on the valence electron only. So let's draw that. So the ground S here is ground state of sulfur, which is 3s2, 3p4. 3s2 and 3p4. 3 and 4. So as what you can see here, at this stage, the ground state of sulfur only has 2 unpaired electrons. So logically, it can only form with 2 fluorine atoms to make bonding. Hence, in order, but we need the sulfur to make bond with 6 fluorine atoms. Here, you can only see that it makes 2 unpaired electrons. So what we're going to do is we're going to excite the electrons from the 1 electron from the 3s orbital into the empty 3d orbital. Here excite to there, here excite to here, the second orbital here. Okay. Hence, this will result in the formation of 6 unpaired electrons. These 6 unpaired electrons will then, as you will expect, it will combine with 6 fluorine atoms. But then 3s, 3p, and 3d is in different energy state. They don't have the degenerate orbital energy. So what we're going to do is we're going to hybridize them together. So we're going to group them together into a much more stable state which is consistent to its molecular shape. So we're going to produce a hybrid orbital. So we will combine the s orbital here with the s combined with the 3p and 2d that contains electron will be combining together to form 6 sp3d2 hybrid orbital. Let me write it that first. So sp3d2. So there are 6 of them. And then we will draw the electrons. One, 2, 3, 4, 5, 6. And then this hybrid orbital will then overlap with the terminal atom of the fluorine. So now we're going to see the orbital diagram of the terminal atom, which is fluorine. So fluorine has 9 electrons, right? So fluorine has 9 electrons. So the electronic configuration of fluorine will be 1s2, 2s2, 2p5. So we're going to focus on the valence electron only, which is 2s2 and 2p5. 2, 3, 4, 5. As what you can see here, you have one unpaired electron. So one unpaired electron will then combine with one of the sp3 orbital. Since we have 6 fluorine, hence we will have everything multiplied by 6. So every time, every single fluorine atom will then combine to each of the sp3d2 orbital in order to form sigma bonding. Now we're going to draw the orbital overlapping of the species of SF6. As what you have seen, S will become the central atom and it has the hybrid orbital of sp3d2, which is 6 of them, and it has 6 lobes, where it carries the shape of octahedral. 1, 2, 3, 4, 5, and 6. Let me redraw this one to be nicer. And 6. Alright. Now, S becomes central atom and we need to label the lobe as well, which is sp3d2. Okay, label it there. 3 of them, 4 of them, 5 of them, and 6 of them. Now, we're going to overlap that with the terminal atom of fluorine. Okay, so we're going to overlap that with fluorine, so we use the blue color. So the fluorine, as what you have seen before, it comes from the 2p orbital. So we have to draw the 2p orbital, which has the shape of a dumbbell. So let's draw here. 1, 2, 3, 4, 5, and 6. So we have to label that with fluorine, 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 and fluorine. And we also have to label the lobe as well, where it comes from. So we have to label that with 2p. Okay, and then the overlapping section here is the area where a bond is being formed. As what you have seen, one electron here will be paired with one of the electron from the sp3 hybrid orbital. One terminal atom will combine with one electron of the sp3d2. And we have 6 of them, so each of their terminal atom will combine to form a bond. So 1 here and 1 here. So it needs to be an opposing spin because according to the Pauli exclusion principle, there's no true electron which have the same set of quantum number, and then it couldn't be on their same arrow because we need to minimize the repulsion, one clockwise and one anti-clockwise. So it happens for every single bonding for SF bond. And as what you will expect, this kind of overlapping is end-to-end overlap, and hence this will produce a sigma bond, which is represented by a green sigma label on the side. As what you can see here, the structure, the overlapping orbital of the SF6 hybrid orbital with terminal atom of fluorine is now complete. If you were to compare that with the Lewis structure that you have drawn, it is essentially quite similar. The difference only the way the way that we write it, because here we wrote it down in terms of bonding pair, but in here we write it in terms of orbital overlap, where the central atom will hybridize the orbital together so that they are in the same energy and consistent to the molecular shape. But terminal atom is remains to where the valence electrons involved in the bondings. So single bond represents a sigma bond, and it is similar to what we have drawn. I hope this is helpful to you, and we will see again some other time. Thank you and goodbye.